Hello and welcome. Today's another lucky day because you're going to be doing exercises 15, 16, 12 and 20 in that order. In the last class, in the last lecture, we were studying the idea of current. This question as to how you quantify the idea of flow. Strictly speaking, I would call this a probability current density, but let me just call it a current. And we derived this crazy formula that, at least when I look at it, makes no sense to me, equation 54. How do you get the probability current J from the wave function psi? Equation 54, we have psi grad psi star minus the complex conjugate of this quantity. Let me just abbreviate that as CC. Now, if I was to have a complex number, let's say we called it Z, these objects are complex conjugates of each other and they're being subtracted. Here's Z conjugate, which is A minus IB. If we subtract them, what happens? If we subtract them, what happens? It's purely imaginary and it's 2B. A minus A disappears. IB minus IB becomes 2IB. What you end up with is twice the imaginary part. Z minus Z star is twice the imaginary part of Z. Oh, sorry, 2I times the imaginary part of Z. So here we've got something minus its complex conjugate. We'll get 2I times its imaginary part times the imaginary part of psi grad psi star. This still doesn't help me, but we get some pleasing cancellations. The 2 and the 2 cancel, the I and the I get together, we get a minus, we get a H cross, we get an M, and the imaginary part of psi grad psi star. This exercise is about the following. It's about being discontent with this formula because it's not physically transparent enough. It's about strengthening that analogy between flow in a classical fluid and flow in a quantum mechanical sense. Now, 1926 was a good year for many reasons, one of which was this was the year that Schrödinger wrote his famous sequence of 4 papers where he developed the Schrödinger equation. But in that same year, Madelung, and you may have heard the name Madelung, more famous in chemistry than physics. For those of you who've done chemistry, you may have met the so-called Madelung constant. In the same year that Schrödinger wrote his famous sequence of papers, Madelung wrote a paper in German, and I'll put it up on Moodle as non-examinable extension material. This paper was called A Hydrodynamic Formulation of Quantum Mechanics. In other words, thinking of quantum mechanics from a fluid perspective. And what he did in that paper was exercise 15 to transform, in what's called now the Madelung transformation, to transform this difficult to intuit formula for the current into something that's more directly intuitable. And he did the following. Let's take that wave function at each point in space, at each instant of time, which I'll suppress. It's a complex number. And complex numbers can be written in terms of their magnitude and in terms of their phase. Now, sometimes I call the phase phi, just for a pointless change of notation. To be consistent with Madelung, let's call the phase S. This is nothing more than writing a complex number in polar form, magnitude and phase. Now, the magnitude is the same thing as the square root of the magnitude squared. And the square root of the magnitude squared is the square root of the probability density. So Madelung said, let's write the complex wave function in polar form and shove it into this expression and see what happens. And what's going to happen is that we're going to see that difficult to intuit expression becomes more directly intuitable. In fact, it's going to look a lot like the classical fluid result that I wrote in the last lecture, but let's do it. And I feel a mental blank coming on, by the way, so I'll be asking you some questions. Minus H cross on M. So I'll do the easy bit, you do the hard bit. Imaginary part of Now, because I'm speaking without notes, I may and probably will screw up, so when I do, please tell me. Psi grad psi star. I don't want to write grad psi star. Instead of psi, I want to write this. Then I want to take the gradient of psi star. What's psi star? Not a trick question. What's psi star that appears here? Beautiful. Square root rho. So we're complex conjugating psi. This is real, so root rho stays as root rho. E to the is, on the other hand, as was correctly stated, the I becomes a minus I. So the general rule when complex conjugating functions is to replace I with minus I and to replace any complex pieces with a complex conjugate. So I becomes minus I, and that's all that needs to be done. Now, this is a formula that's too big for me, so I want to focus on this piece. And at this point, I'm madly trying to remember some vector analysis, and I'm forgetting some vector analysis. So I want to work towards what the hell to do with this. If I was to have a product of functions a of x and b of x, and suppose I was to differentiate that product of functions, because this is in essence asking us to differentiate a product of functions, and that product happens to be root rho times e to the minus is, but it's a product of functions. How would I differentiate this product of functions? Any words pop into your head? Chain rule. Very close. Product rule, beautiful. This is a product of functions. And so we use a product rule. We differentiate the first thing, leaving the second alone, and we differentiate the second, leaving the first alone. Fair enough. This is differentiation of a product of functions with, let's say, a d by dx. Let's make this slightly fancier. Let's differentiate a product of functions. A will now be a function of x, y, and z, and b will now be a function of x, y, and z. But instead of differentiating with respect to x, we differentiate with respect to x, y, and z in the sense of a gradient. Now, you might be trying to madly remember a second-year vector analysis formula. Don't. Just have a guess, have a stab. What do you reckon this is? So leave the first thing alone, differentiate the second, differentiate the first thing, leave the second alone. What do you reckon this might be? It's the same, yeah. When you've got one derivative, you stick it either on the second or on the first. You've got one derivative, you either stick it on the second or you stick it on the first. And I put brackets around here just to make it clear that this grad acts on the A. Now this is a vector. This is a product of scalar functions. Gradient will turn that product of that scalar into a vector. This is a scalar times a vector, that's good. This is a vector times a scalar, which is a vector. So each term here is a vector. By the way, notice that here you have one grad, here you have one grad, here you have one grad. This is a conservation of grads, right? Just like conservation of dashes, 1 dash, 1 dash, 1 dash. If there was a dot there, you'd have conservation of dots as well. Now this is on the one hand flippant, but it's a very, very good way to remember formulas that you don't remember, right? So this is a gradient of a product of functions. So we're getting closer to being able to differentiate this. Now the chain rule was mentioned earlier, and the chain rule is actually useful here, right? Because we're sensing some vector analysis wizardry being needed here, and again, you see me mercilessly using vector analysis, but trying to make the analogy between vector differentiation and more ordinary scalar differentiation. The chain rule was mentioned, so if I had some function, let's call it f, or better still, let's call it rho, and suppose it was raised to the power of a half. Suppose I was to want to differentiate this, d by dx of this object. So let rho to the half be a function of x. How would I differentiate it with the chain rule? I'd have half rho to the minus a half. Yep. I'd have half rho to the minus a half, and then d rho dx. you apply the chain rule. This is nothing more than the chain rule. If I was to have the gradient, on the other hand, of a function such as root rho, the gradient of rho to the half is exactly the same thing. Yep. Half rho to the minus a half. So I remember most of these vector analysis formulas just by way of analogy with the 1D version. The differentiation, it's conserved, right? Differentiated once, differentiated once, differentiated once, differentiated once. Now you can prove these formulas to yourself by doing it the long way with the chain rule, but this is what you'll get. Direct analogy with one dimension and three-dimensional differentiation. So we know how to use the chain rule to differentiate things like this with a gradient. We know how to use the product rule to differentiate products. Here we're going to need to do both things. Yep, here we're going to need to do both things. So again, let's focus on this thing that's underlined, the gradient of root rho e to the minus is. Because this is what's standing in our way of calculating this formula here. And I want to do this in pieces. I note that this is a product of two functions, so I want to apply the product rule. Yep. Take the grad of the second thing, leaving the first alone. Take the grad of the first thing, leaving the second alone. And I can do it in either order, so let's differentiate the first object, leaving the second alone. Or we can leave the first object alone and differentiate the second object. That's good. We already know how to do this with the chain rule. Don't look on the left. This is grad of rho to the half, which will be a half rho to the minus a half, grad rho, times e to the minus is. Now the thing on the right, we've got a root rho and a plus sign. And we need to differentiate this. And I've forgotten the formula, but that's fine. Go back to 1D. If I have e to the x and I differentiate it, I get e to the x. If I was to have e to the ax, where a is a number, I would have a e to the x, e to the ax. If I was to have a function here, I'd apply the chain rule and I'd have a dash. In fact, yeah, I have a dash out here. And if I was to have a gradient, exactly the same thing. What you shove out the front is the derivative of the exponent. That's how to summarise all these things. When you differentiate e to the x, what you shove out the front is the derivative of the exponent, which happens to be 1. If I have e to the ax, what I shove out the front is the derivative of the exponent, which is a. And if I have a as a function of x, what I shove out the front is the derivative of the exponent, which is the derivative of the exponent, a dashed. Same thing here. What I shove out the front is the gradient of the exponent, in other words, minus I grad s. Again, if you're lost at this stage, and if I was in your shoes, I would have been, because I would not have revised my second year vector analysis, please do so. It's one of the main components of the language of nature. So we've expanded this horrible thing that appears here. So we can now continue with our formula. This is what we want. And by the way, we're feeling a bit pessimistic at this stage, right? We're doing this. Imagine you're Madelung doing this in 1925 to publish in 1926. You're trying to simplify this formula, and it's getting worse. Unless it collapses down to simplicity, this will be a trial and error dead end. So let's see what happens. Minus h cross on 2m. Root rho e to the is. Sorry, imaginary part. We've got a root rho e to the is. And now I need to write all this stuff. Now, I could just put a bracket there and write out all this stuff. Is there something I could do to make my life a little bit easier than just putting a bracket here, open, close bracket, and writing out all this stuff? What could I do to make my life a little easier? Factorise, beautiful, that we notice that there's a common factor here. So let's factorise out e to the minus is. Let's factorise out e to the minus is, and we see a cancellation immediately. When things start to cancel, you often know that you're on a good thing. We've factorised out e to the minus is, and we get half rho to the minus half root rho. And we get this object here, minus I root rho grad s, and that's it. So we want to take the imaginary part of this thing. What can I do next? Besides hope that I haven't screwed up.
Get rid of everything except the imaginary part.
Beautiful. Get rid of everything except for the imaginary part. We're taking the imaginary part of all this stuff. Anything that's real goes as well. Fantastic. So lots of cancellations, we're feeling good. So we've got minus h bar on 2m. Again, I'm hoping I haven't screwed up. We've got a minus sign, which turns that into a plus. We're taking the imaginary part, so that I goes, and we've got root rho grad s. Beautiful, there's another root rho here. So we bring them together. Thank you, appreciate that. There's another root rho. Root rho gives rho, and then we have grad s. This is it. Is there anything else that needs to be done here? Or anything else that I've left off?
Didn't we want the imaginary part?
Didn't we want the imaginary part? So the answer is yes, we did. So we're taking the imaginary part of this object, but the imaginary part of a complex number is real. So the imaginary part of so we're keeping the imaginary part, but the imaginary part of the complex number is real. So we have this expression here. Now, I suspect I've made a mistake somewhere and I can't see where. I don't believe that 2 should be there. Can anyone see where that 2 came from?
Up to the top board, at the final line, the 2s are cancelled, but then in the second board, you brought it back.
Beautiful. Thank you. So I've screwed up. This is good, and well done for picking it up. So the statement was that here the 2's cancel. There's no 2 in the denominator here. But then when I wrote down this formula, the 2 came back. This 2 should not be here. So please delete this 2. Having deleted this 2 that appears here, we delete the 2 that gets carried through at this point. This 2 shouldn't be here, and this 2 shouldn't be here. Thank you. So we now get the current is h bar on m, probability density, grad s. And let's now compare this. This is quantum mechanics. Madelung's paper was called Quantum Mechanics in Hydrodynamic Form. Classical mechanics, this is the classical mechanics of a continuous fluid such as water. You would have the current density equals, this is now the density, kilograms per metre cubed, times the velocity. Again, at some point in space, you fill the room with boiling water. V is the direction in which the particles are flowing, their velocity, more precisely. But the denser the fluid at each point, the bigger the current. The faster the fluid is flowing at each point, the bigger the current. So let's stare at these formulas until they begin to speak back to you. So let's stare at them. I want to ask a deliberately vague question, which is, what thoughts do you get, or what words are said to you when you stare at those formulas? What physical concepts leap out, or what appears in your head? As always, there's nothing wrong with being wrong. Yep.
B equals h bar and
Beautiful. But let's make these formulas the same, right? h bar on m grad s is the velocity. This is the correct formula. No, it wasn't in the notes, but bugger the notes, right? This is the formula for velocity in quantum mechanics. You have some wave function, psi of RT. You can represent it in Madelung form as root rho e to the is. And I'll leave off the RTs, right? This is the phase. If you were to have some source, for example, emitting electrons, these would be the surfaces of constant phase. Sure, if you had a plane wave, the surfaces of constant phase, constant s, would be wavefronts. These are surfaces of constant s. What would these surfaces be called in second year vector analysis? What would these surfaces be called in the geography map? Contours, beautiful. So these are contours in a geography map. In the context of second year vector analysis, these will be called level surfaces. These are surfaces of constant s. In what direction does grad s point? Whether you're doing geography or vector analysis?
Is it normal to?
Beautiful, absolutely. Grad s is normal to the surface. At every point, grad s is normal to the surface. Since s varies with position and time, grad s will vary with position and time. The formula in the top right says that the velocity as a function of position and time, let's put it in, is some constants times the gradient of s, which will be proportional to the surfaces of constant phase, to the level surfaces. Since the surfaces themselves fluctuate with time, these vectors will fluctuate with time. If these level surfaces get closer together, grad s gets bigger. If the surfaces of constant phase get further apart, grad s gets smaller. Now, I want to emphasise again, I'm not a physics genius. I have to work very, very hard to understand stuff. I look at this formula and ask myself the question, why is it obvious? It's not an arrogant question. If you understand something deeply enough, then when you get to an answer, you should be able to stare at it and say, why could it not be any other way? Again, I'm asking a deliberately vague question. What is obvious about this formula? In retrospect, that is.
The derivative of displacement is velocity.
Beautiful. The derivative of displacement is velocity. The derivative of displacement is velocity. Excellent. Why is the m on the bottom? By the way, no quantum mechanics book will ask these questions, let alone answer them, but that shouldn't stop us. Why is the m on the bottom? Mass resistance acceleration, definitely in the right direction. Do you want to elaborate? No, that's cool. No, that's cool. But absolutely along the right track. If every electron was suddenly twice as heavy, ... That slow down? Yes, in the following sense. I know I was bagging this formula before, but in essence, grad is momentum, right? And we learned that if you sandwich grad in between psi star and psi, you get and integrate, you get the expectation value of momentum, right? So the expectation value of momentum is the integral over all space of psi star times minus I h cross, bugger that off, and just have the grad. Okay, I'm not interested in constancy, I just want to get to the essence of things. This is how we calculate the expectation value of momentum. This is a little bit like the momentum at a point. So when you sandwich grad between psi and psi star, okay, never mind the imaginary bit here, I'm just trying to get some physics, some intuition for this in retrospect. It's a little bit like the local momentum, but that's so close to the idea of velocity, right? It's so close to the idea of velocity. But if you double the size of your billiard balls for a given momentum, you halve the speed, right? This is where this m comes from. So what you're saying was absolutely correct. If we think of this loosely as the local momentum, I haven't explained where the imaginary part comes from. That's something for you to consider. But what I'm doing here is more important, in general, is more important than the particular thing we're doing, which is learning to look at results and ask, how do you believe them? Do you believe them? Are they intuitively obvious? If you think about them hard enough, what physics do they elaborate? And this quantum mechanical formula is the same as the classical mechanics formula if you make this identification. And this is, by the way, the velocity operator in quantum mechanics. All right. So we now just have the current, whether you're talking about classical or quantum fluids, is rho times velocity. We understood this from a fluid mechanics perspective, exactly the same formula from a quantum perspective. That also makes another important point. When you see something like the continuity equation for the first time, it looks kind of bizarre, and I pull these tricks with Gauss divergence theorem and so on. But when you see it for the 15th time, in the 15th different context, then you realise it's a very, very general equation. And when you see me use the same trick for the 10th time in solving quantum problems, it goes from being an unfamiliar tool to being a familiar tool that you can use as needed. Developing the intuition for when to use tools takes time, practice and sweat. So much for exercise 15. Let's move on to 16. And again, we're going to have an interplay between concepts and mathematics. So what we want to do here is to have a monoenergetic wave function of the form given by 44. So this is a special wave function of a particular energy. I could put a capital E subscript here, but I won't. We know that if you have a wave function built up of plane waves only of a particular energy, that it can be written in this form, where E is its energy, and this is a spatial wave function. Fair enough. How do we write this in Madelung form? How do we write this in terms of a magnitude and a phase? Again, I'm having a bit of a blank, but I want to massage this into the form given here. So how do I write this wave function in polar form? How do I write this wave function in polar form? How do I write it in polar form? So denial is an excellent technique when solving problems. This thing confuses me, therefore ignore it for now. Pretend it's not there. How do I write this in polar form? Let's have more denial. This is a single complex number psi. How do I write it in polar form? Not a trick question. You don't believe me, do you? All right. Single complex number psi, we can write in terms of its magnitude and in terms of its phase. Let me call the phase phi. That's a single complex number psi. Argand plane, real, imaginary. This is a particular complex number psi. The magnitude is the length of this vector, magnitude of psi, and phi is this angle, this polar angle. The fact that psi depends on position, fair enough. Psi depends on position. It's still the magnitude of psi, except that now happens to vary with r. And that phase still depends on r, but exactly the same thing. And then we have this thing that I ignored. So just put it in there. Again, the trick I pulled earlier, this magnitude is the same thing as the square root of the magnitude squared. So that's root rho. That's root rho. How about these two exponents? What can I do with them? Beautiful. Add their arguments. Excellent. Now you see why I changed the notation, because this thing is the same thing as S. This is in exactly the same form as this boxed equation, with S equaling phi of r minus, etc. And this was a function only of r, hence this is a function only of r. So the phase of the complex wave function is some function of position minus a certain function of time. So let's now solve the question, which is to ask for this so-called stationary state wave function, what does the current look like? The current, which is in general a function of position and time, is h bar on m root rho. In this question, what does rho depend on? Rho is a function of r. That's correct. Why is there no t here? Steady state, beautiful. There's no t here because it's steady state. There's no t here because this thing had no t because it's steady state. So we've got this part of the formula, h bar and m rho grad s in the top panel. But then we have grad s. That's what we want to do now, to take the gradient of s. And s is phi as a function of r minus this. How do we continue? Sorry? The question is, should there be a square root? And the answer is no. Thank you. This square root shouldn't be here. Thank you. What should we do next? Now that we've corrected my mistake, and thank you. My hint is to look over this side of the board.
The ET on H bar doesn't involve the grad, or the grad doesn't involve that. So the cancel to zero, there's no derivative there.
Beautiful. So the answer is that this is differentiating with respect to position. This is independent of position. There's no x's or y's or z's here. So we cross this off. At that point, there's no t's on the right-hand side. Yep. Since there's no t's on the right-hand side, the current is now independent of time. Yep. So the current is independent of time. So J, in general a function of position and time, is now just a function of position. What's the fluid mechanical analogue of this? A current that's independent of time. Steady state flow, yep. So this is a quantum mechanical equivalent of steady state flow. I have my fountain. There's steady state flow. You take a picture now, you take a picture later, it's exactly the same. The current is independent of time. This is a quantum mechanical equivalent of steady state flow. So if you were to fill this room with a wave function of a particular energy, its quantum mechanical flow would be independent of time. What will be the visible light analogue of this? It will be to fill the room with red laser light, light of a particular energy, light of a particular colour, red laser light. This is saying that red laser light can't change with time, which is wrong. I can wave a laser pointer around. The answer is that if I'm waving a laser pointer around, this tells us that steady state flow is synonymous with a single energy being present. In the context of quantum mechanics, it's also true in classical optics. When I wave my red laser pointer around, there's actually a spread of wavelengths. It's not strictly one energy. When you have strictly one energy present in quantum mechanics, you have steady state flow. When you have strictly one energy present in classical optics, if you fill the room with red laser light, which has exactly one energy, that's the proviso, then it must fill the room for all time. Steady state flow. I mean, this is a very strong thing, right? This thing's independent of time. You wait 1 billion years, it doesn't change. That's the true meaning of steady state flow in this context. As always, everything I do is wrong in the sense that everything I do involves an idealisation. You know, I say steady state flow and then I extrapolate, right? Think of the lemon tree, right? I extrapolate and say, well, that's steady state flow. 1 billion years hence, it's the same thing. I've tried to extrapolate too far. Again, there's always caveats, but the point is this is steady state flow. It's within, within a particular period of time. What's next? Exercise 12. Now, I've done these in a particular order, which had some sense for me at the time. So let's move to exercise 12. Okay, so exercise 12 is about proving the Schrodinger equation preserves the normalisation in time of the wave function. Now I've forgotten what that means, so let's remind ourselves. What's this? Probability density. This is probability per unit volume multiplied by volume. So this object here is the probability that you'll find an electron within some volume dx dy dz, which I call dr, at the position vector r of time t. This is the probability of finding an electron anywhere. And if this is a one electron wave function, then this thing better be 1. But now the question comes, we've got the Schrodinger equation, which is a partial differential equation for the wave function. You could ask the question, I give you the wave function at some initial time, t equals 0, and I give you the Schrodinger equation and say, okay, this is total knowledge of the system at t equals 0, solve the Schrodinger equation to propel this into the future, to some future time, t equals t, which is greater than 0. Yep. But you now ask the question, suppose that this normalisation condition were true at t equals 0, does the Schrodinger, and this is called a normalised wave function, this wave function is normalised at t equals 0. Question, if you evolve the wave function into the future, if you make the wave function grow old according to the Schrodinger equation, we'll learn how to do this soon, is this thing normalised? In other words, if this is true at time t equals 0, is it true at arbitrary time? And that's what the question is asking you to answer. So if I was to succinctly ask the question in one sentence, it's as follows. Does the Schrodinger equation preserve the normalisation in time of the wave function? And the answer is it must. If it doesn't, then your theory is screwed and you've got to start from scratch. So it's an important question. I mentioned in the last class that you should not follow my solutions in the sense of solve your problems your own way. I always encourage you to solve problems differently to the way I do, and I myself solve my problems differently to the way that I've solved them previously. Again, I was looking at my solution to this problem. Does the Schrodinger equation preserve the normalisation in time of the wave function? And I didn't like it, so here's a better way. We learned in the last lecture that the Schrodinger equation implies the continuity equation. Current density J, probability density rho. We know what this means by applying the Gauss divergence theorem to it, as we did in the previous lecture. We want to beat a path from the Schrodinger equation to the preservation in time of normalisation. This is the place to begin. Now I ask you with hope, what do I do next? And remember, when I ask you these questions, you should fire back with the answer to yourself. What could I do next? Again, almost every problem is unique in quantum mechanics. That's frustrating, but it's also part of the charm. Ask yourself, what could you do? And a trial and error mentality could just say, what could I do? Often there's only 2 or 3 things, just give it a shot and see what happens. What could you do to this equation to continue? Could you make rho equal to 1 because of normalisation? Unfortunately, no, that normalisation says that the integral of rho over all space is 1. But what you've just said, could you make rho 1 because of normalisation, is part way towards the answer, or an answer. You ask, could you make rho 1 because of normalisation, and I point out that it's actually the integral of rho that's 1 because of normalisation. What subsequent idea could that spawn? Going from here to here, I've injected an integral. Beautiful. So integrate over all space. Because you sense, and you sense correctly, that the fact that rho is normalised, its integral is 1, is somehow the key to the problem, and that's actually the swiftest way to answer the problem. Notice also how an answer that's actually strictly speaking incorrect, sometimes you can be profoundly wrong and you're wrong in a profound sense. You can then morph it into something that's right. That happens so often in physics. As one example, the so-called Klein-Gordon equation, which is an equation of relativistic quantum mechanics, was derived through such a process. All right, so let's integrate this thing over all space. And I want to be slightly fancy in the way that I integrate this over all space. I want to have some lump of space, omega. This is going to be a volume, some bounded volume, bounded by a smooth surface. And I'm going to make this volume, this piece of plasticine, fill the whole universe. So to integrate over all space, I'll begin by integrating over this volume, and then I'll make that volume fill the whole universe. So we integrate over this volume, the divergence. Again, we want to prove that the Schrödinger equation preserves the normalisation in time. I'm taking the continuity equation as a starting point because I know it's derived from the Schrödinger equation. So I integrate over all space. Integrate over all space, d rho dt. And we know that this all equals naught. Yeah, that equals naught. So if you integrate over all space, you're still going to get naught. What could I do next?
With the final term that you take for the commutes, take out the differentiation and then differentiate one.
Yep. So yes, but so yes. So let's pull out the d by dt. Let's interchange the order of time derivative and integration. Right. Integration is nothing more than sum. If I have f plus g and differentiate it, the sum of the derivatives and the derivative of the sum is the same thing. You can interchange the order of summation and differentiation. Again, this is s for sum. That's what an integral is, a continuous sum. Interchange the order of d by dt in the sum. Excellent. How about this first term? So the second half of your answer is absolutely correct, but I need to be a little bit slower to work towards it. So could we just park the second half of your answer, correct though it was? And let's look at the first part. This is the integral of the divergence of something. What word appears in your head when you integrate a divergence of a vector field over some region? Gauss's theorem, beautiful. By the way, I think I mentioned that I learnt a lot of mathematics from Russian textbooks because my first supervisor was Russian. One excellent thing about Russian textbooks is that you'll find that most of the theorems of mathematical physics are named after Russians. So it's not called the Gauss theorem, it's called the Ostrogradsky theorem. And by the way, I wonder why that grad's there. But yeah, that's kind of a funny thing. I actually don't know who discovered it first. Anyway, divergence theorem. So if we integrate the divergence of the current vector over any vector field, well behaved, over a volume, what you get is the flux. Now I can write that in the fancy way I did in the last lecture, but it's just the flux of J through the boundary of the surface, which I'll call del omega. Now, you mentioned integrate over all space. In other words, take the volume of the ball, take omega to fill all the space. What's the flux of the current vector through the boundaries of the known universe? What would a physicist say to the question of what is the flux? So I've got a wave function. I've got an electron in my finger, right? I've got an electron in that air conditioner that doesn't work. I've got an electron in the piece of chalk, and I describe it with a wave function, and I ask you the question, what's the flow of this thing through the boundaries of the known universe? The answer would be 0. Because?
Because it can't exit the universe.
Because it can't exit the universe. Excellent. A second way of looking at this, if I was to look at it from a mathematical perspective, I'd say, okay, let this be a spherical surface. That surface is growing as radius squared. If the flux vector, whatever it is, decays faster than 1 on r squared, then the flux through that surface will be vanishingly small. Physically, there's no electrons at the edge of the known universe, or in particular, the electron in the chalk or my finger or the air conditioner isn't flowing through the edges of the known universe. And so this flux through the boundary of this arbitrarily large surface is naught. So we get d by dt. And this object here is the probability of finding the electron somewhere. We're now integrating over all space, so let me just write a triple integral over all space. Again, if I was to omit the limits, this would be an integral over all space. This is the probability of finding the electron anywhere, and that's independent of time, which takes me to your point, that if this thing is normalised, if this object equals 1 at a particular time as it does, and this is a constant of the motion, this is a constant of time, it's independent of time. If it's normalised at any one time, then as a consequence of the Schrödinger equation, it's normalised at every time. So this completes the proof that the Schrödinger equation preserves the normalisation in time of the wave function. I think I'll stop there. Thank you. As always, happy to answer questions after class for as long as you like.